Thanks. So, but we're looking forward to starting off with Astha. So we had Michelle, Astha's PhD supervisor, I think, just before the end of sort of June last year. This is a continuation of that. I think I said at the, when Michelle talked, when I did my doctorate, I know I go to a conference, and somebody who was working on low brightness galaxies put on it was a days of acetates, put an acetate on the display and you could see some stars. And he said something like, there are 150 dwarf galaxies on this slide. And of course, all us theorists, none of us could see anything. So I've always been very interested in low brightness surface galaxies. And with that,
thank you so much for introducing me, Collins. So yeah, I'm a PhD student. I just started like 6 months ago, and I'm very thankful to the university for all the opportunities that I've gotten to showcase my work so far. And this is one of the opportunities. I'm very glad that this is the one science communication opportunity that I signed up for, and it had given me a lot of confidence coming to the stargazing events organized by the Guildford Astronomical Society with the University of Surrey. It was a great pleasure meeting a lot of great people. And then Michelle suggested me that I should also do one of the science talks. So I was like, why not? For sure. And yeah, title, although it looks very complex, I would try my best to make sense of it for you guys in the next 1 hour. So we will start now. Okay. So yeah, you can turn off the lights. It's okay. All right, everyone. Have you ever looked at the night sky and wondered that there must be something more out there which your eyes cannot see? Because there surely is. And that something is so faint that it makes Surrey on a cloudy night like this look bright. Today, I will be taking you to the faint edge of the universe, and we will be talking about the ultra-faint dwarf galaxies. Too many terms involved in the title. Let's break them down one by one. First of all, what is a galaxy? A galaxy is defined as a huge collection of gas, stars, dust, and planets held all together by the force of gravity, giving you a structure like this. However, when we scientists were investigating how fast the galaxy is rotating as we move away from the distance of the center of the galaxy, we find out that our observations are not matching with the calculations. Here you can see that the measured rotational velocity of the galaxies is very high as compared to the calculated curve, which is very low. So what is up with the galaxies, which is making them rotate so fast? Well, investigating the reason for it further, scientists came to the conclusion that the galaxies, the amount of mass that has been measured for the galaxy is not sufficient to hold the galaxies against such a massive rotational speed. So there is a need for an additional component of mass. So what is this additional component of mass? Well, we don't know much about it. And when we scientists don't know much about a particular stuff, we like to put the word dark in front of it. And hence, it is called dark matter. I don't know why it is doing this weird flash, though. So not only dark matter is an important component of the galaxies, it is a very important component of the entirety of the universe. When you look at the composition of the universe as a whole, all the stuff that you have seen, touched, and felt so far makes up of only 5% of this entire universe. More than a quarter of the universe is dominated by dark matter, whereas dark energy makes up of 70% of the universe. So dark energy can be topic of for maybe some other of my presentation with the Guildford Astronomical Society. So when I now ask you to close your eyes and imagine what a galaxy might look like, the chances are that you might imagine galaxy as a gigantic spiral full of billions and trillions of stars, much like our home galaxy, Milky Way. So talking about our home galaxy, Milky Way, it contains 100 billion stars. And if the Milky Way will be positioned in the same position as sun in the night sky, it will shine as bright as 100 billion suns. Talking about the amount of dark matter in this galaxy, Milky Way contains 21 times more dark matter as compared to the luminous matter, that is all the stars, gas, dust that is present in the galaxy. That can be visualized by the beautiful cupcake that was in my office one other day. So if the sprinklers on the cupcake, the star sprinklers, they are the baryons, that is all the gas, stars, and dust, dark matter will be the entirety of this cupcake. However, not all the galaxies are like Milky Way. The galaxies, they come in various shapes and sizes. And some of the most smallest and the most elusive ones are these ultra-faint dwarf galaxies. In comparison to their bigger cousins like Milky Way, which contain like 100 billions of stars, these galaxies contain like thousands to 10,000 stars only. When positioned in the night sky and comparing their brightness with the Milky Way, it will be 100 million times less bright than the Milky Way. However, they do not lose every race against Milky Way. When you compare the amount of dark matter in these galaxies, the amount of dark matter can be 500 to like 600 times as compared to the luminous matter. So this is what these galaxies look like in a beautifully lit night sky in Atacama Desert in Chile. And here you can see 6 of these ultra-faint dwarf galaxies, Reticulum, Pictorius, Tucana 2, etc., along with the 2 satellite galaxies, Large Magellanic Cloud and Small Magellanic Cloud of Milky Way. Even in such a beautifully lit light sky, you can see that these galaxies appear to be coming from a completely dark patch. This is how small and this is how faint these galaxies are. This is the picture of these galaxies against the background of Milky Way. So Milky Way here is located edge on. And here you can see, again, these galaxies distributed around Milky Way along with the Small and Large Magellanic Cloud. These galaxies are so small that if they ever happen to go on a head-on collision with Milky Way, there is absolutely no chance of their survival. So then the question arises, how are these smallest galaxies so important? These galaxies are important because not only they have very small mass and oldest ages, they also have a very, very simple structure, which makes our life easy when it comes to understanding the galaxy evolution. So the fact is, like smallest masses and oldest ages, we can calculate them by observing these galaxies. However, the evidence of simple structure can be obtained by comparing the image of Milky Way, our gigantic spiral, very beautiful, with one of the ultra-faint dwarf galaxies, Tucana B. So when you compare the structure of Milky Way with Tucana B, you can see that Milky Way is appearing as a gigantic spiral, again, with billions of stars, and has a lot of patchy appearance. However, when it comes to Tucana B, it appears just like a blob of stars. So what is the reason that the Milky Way has a lot more patchy appearance as compared to Tucana B? Stars, they are just like humans as they live and they evolve. They have their own carbon footprint. And the carbon footprint of the stars is in terms of the dust and the gas they release as they evolve. So what happens with the Milky Way is that it contains like billions and trillions of stars, and they evolve entirely in the system. These billions of stars, as they live, they release a lot of dust in the surroundings, which is all captured into the spiral arms of the Milky Way, giving it this appearance. So what it does for the Milky Way is that it changes the initial composition of the material available for evolution and birth of the future stars. So when now the future stars will be born, they will also have the material influenced by the dust from the stars that have lived previously. So that makes the evolution of galaxies like Milky Way very complex. However, when it comes to Tucana B, there are still a lot of stars present, but it is not 100 billion, right? It is just 1,000 to 10,000 stars. So there is not a lot of carbon footprint of the stars, which is present in here, and thus its evolution is relatively simpler. So there is this one fact that galaxies like Milky Way contain a lot more stars as compared to Tucana B. The another thing is that Milky Way is a really, really big galaxy. It is 100,000 light years as compared to Tucana, which is just 260 light years, which makes Milky Way more prone to collision from other small galaxies like Tucana, and even the bigger collisions like the way it is about to collide with Andromeda. So all of these collisions, the increased probability of collision due to the big cross-section area makes Milky Way evolution more complex as compared to the small galaxies like Tucana B, which can be there sitting in a portion of the night sky for a lot of like 1 million years. So due to these factors, these ultra-faint dwarf galaxies, they are very sensitive to the galaxy formation physics. So much so that we can observe the effects of individual events which are impacting the galaxy, such as supernova and galactic outflows. So what is a supernova? Stars are also like cars. They need fuel to burn. They are churning all this hydrogen in their core, burning it into helium, and further on till they go up to iron. And after iron, most of the stars, they are not able to hold themselves up against the massive pressure of gravity. So what happens with the stars is that they collapse themselves under the force of gravity, and the star bursts in a fantastic fashion of light, which is called a supernova. So what happens with the supernovae is that it releases a lot of processed material from the stars to the surroundings, thus changing the initial composition of the material very close to the supernovae. It also heats up the surrounding of the stars a lot more. So it changes the initial composition of the material, it heats up the surrounding, and also the winds of the supernova energy to push a lot of material away from the vicinity of the supernovae. And what happens with the supernovae is that winds of the supernovae, they catch up to one another. It leads to this massive galactic outflows, which have the ability to just take a lot of material from the galaxy. So supernova can heat up the surroundings. It can lead to the winds, which can lead to the galactic outflows that can push a lot of material out of the surrounding. And the events like this, they can completely completely stop the star formation, which is happening in the ultra-faint dwarfs. And it is easier to see in these ultra-faint dwarfs because these ultra-faint dwarfs are very small systems. So like one supernova happening can blow away enough gas and dust, or one galactic outflow can blow away enough gas and dust to completely stop the star formation. And hence, these smallest galaxies, they offer us a unique opportunity to test for the galaxy formation models. So how do we test for the galaxy formation models? So much so as to how we test for anything in physics in general. We start with a set of initial conditions. And in terms of calculation of the universe, the initial conditions, we get it from the cosmic microwave background. It is the first bit of the universe, and that has been taken 300,000 years from the Big Bang. So all the initial fluctuations that you can see in the image, these are all the density fluctuations. They give us an initial idea about what the universe looked like, and hence give us the initial condition. Once we get those initial conditions right, we have an idea about how the laws of universe work in general. So, which comes under our simulation methods. So with our initial conditions, coupling it with our simulation methods, we build our simulation suits. Once we build our simulation suits, as per our understanding of the universe, we get some data from the simulations, and then we compare the data from the simulations with the observations. Comparing the data of our simulations, that is our calculations, with the observations sometimes can give us new results, like the discovery of dark matter, as we talked about. Or often it helps us in constraining the models of cosmology, galaxy formation, and black holes, etc. So what we do is we run through this loop again and again, and this loop informs us more and more about our models, improves our models, and tells us more and more about all the cosmology, galaxy formation models, and the black hole physics. So how do we do it when it comes to the ultra-faint dwarf galaxies? Let's start with the observations. So in terms of the observations for these ultra-faint dwarf galaxies, because these galaxies are very, very small, we need really, really big telescopes, just like the one being used for Sloan Digital Sky Survey. This is a 2.5-meter telescope located in Mexico, and it is surveying 1/3 of the northern sky, taking beautifully colored images. This telescope has been responsible for increasing the number of discovered ultra-faint dwarf galaxies from barely like 10 and shooting it up to 20 and 30. So it is very powerful. So one thing is that we take really, really big telescopes. And the second thing is that we keep the mirror of the telescope open for a very, very long exposure time. As the members of the Guildford Astronomical Society must be experts about it. So leaving the mirror open for a long time gives us a long exposure time, and hence can make our image more detailed from the one that you see above to one that you see below. So big mirror, big exposure time. Once we get the data, once we get basically the photons from the telescope, the photons are stored in the tiny chips called CCDs. And the data from the CCDs is then sent for the observations, is then sent for the measurements and some of the analyzations. The general tool for analyzation for the light from the galaxies is using spectroscopy, where generally a prism is placed to split the light that we get from the telescope into the different constituents. This different constituents and this action of splitting the light can tell us more about the composition, the motion, and other parts of the galaxy. So soon, the big player in the observation for the ultra-faint dwarfs is going to be Vera Rubin Observatory. It will be located approximately 2,500 meters high in northern Chile, and it is successor to a long tradition of sky surveys like SDSS. So SDSS was observing the northern portion of the sky. This Vera Rubin Observatory, it will be observing the southern portion of the sky. And it houses Simon Yee Survey Telescope after a couple who donated $20 million for the telescope. A fun fact is also that Bill Gates also donated for this telescope. It was $10 million, so he couldn't make up the cut for getting the telescope named after him. So this is the massive mirror of the telescope. The one that you see here, it is an 8.3 meter big mirror, one of the largest mirrors that are ever present on the Earth to observe these galaxies. And talking about the quality of telescope, the quality of the images is going to be as high as the power of 300 high-quality smartphones, capturing just one portion of the night sky. They have just finished the construction of the camera close to the end of the May. And this observatory is expected to start operations in 2025. In this image, I will show you a kind of cartoon for how this Vera Rubin Observatory will sample the entire portion of the northern sky. So this is how it will take the different pixels of the images. One image is going to be a massive resolution of 3,200 megapixel. And it can survey the entire southern sky in 3 days. So it will generate terabytes and terabytes of data for us. So what Vera Rubin has promised for us, the ultra-faint dwarf galaxy physicists, is that it has promised us that it will help us in uncovering all the ultra-faint dwarf galaxies that are around Milky Way. Also, one very important thing, the naming of the telescope has been done after Vera Rubin. It was an exceptional American astronomer. You remember we discussed about the rotational velocity of the galaxies? She was the person who found out and who derived all the rotational curves of the galaxies, which finally gave us the evidence about the nature of dark matter. And despite facing all the sexism and skepticism that she can face in the field of astronomy as a woman, she did really great work. And these are some of her pictures that are my absolute favorites. In the picture below, you can see that she's very young, like probably 11, 12 years old, looking through a telescope that she had constructed himself using cardboards and other stuff with the help of her father. So she was really exceptional for the time. So yeah, as I said, Vera Rubin has promised for the ultra-faint dwarf galaxies that it will find all the ultra-faint dwarf galaxies around Milky Way. So as of now, there are some 20 plus confirmed candidates, and now the number with it is expected to increase close to 50 and even more. It is expected to start operations in 2025. So once we have our observations ready, then we turn to simulations. And now, who is the big player in the simulation? We at University of Surrey are very big players in the simulation for ultra-faint dwarf galaxies. And this is what I'm working on, actually. So I work on the software Edge, the full form for which is Engineering Dwarfs at Galaxy Formation Edge. And it is a collaboration. It is a simulation suite collaboration between Lund University, UCL, and University of Surrey. So what it does for you, this software, is that it simulates a small box of the universe for you, and it simulates the ultra-faint dwarf galaxies in that universe for you so that you can get the data directly from the simulations. Here, I'll show you one box of the simulation suite. The length of the box is 163 million light years, which means that going from one edge of the box to another, it will take light 163 million years. So all the small dots that you see in here, they are all very, very small galaxies. The big blobs, they can be clusters of galaxies that can be seen. And in this simulation box, everything is happening. Stars are forming, dying, the feedback mechanism happening, supernovae blowing, and everything. So how do we get the ultra-faint dwarf galaxies from these simulations? Somewhat like this. So we started with close to 50 megaparsec, and now we have zoomed to 10 megaparsec. And this is how the different ultra-faint dwarf galaxies have been identified from the simulation suits. We call them halos, like Halo 1445, 1459, very boring naming, but it has been the way it is. So you can see that these galaxies, even after zooming into 10 megaparsec, they appear to be coming from completely dark patches in the simulations. And the masses of these galaxies, again, are not very big. They are 10 raised to power 9 solar masses only. So to analyze anything about these galaxies using the simulations, what we have to do is we have to zoom in way more, zoom in into these tiny regions and zoom in into the galaxies to learn what are the mechanisms affecting the evolution of the galaxies like supernova. So we need to resolve the effect of the supernovae in these galaxies. But that is one of the strongest suits of the edge simulation. So with edge simulations, we can go from massive 163 million light years to resolving the effect of supernova up to 10 light years. That's how powerful the simulations are. So we get the data from the simulations as to what is the metal content in the galaxy, how much is the iron present in the galaxy, what is the age of the respective stars which are present in the galaxy, and stuff like that. And then we compare the results of our simulations with the observations and all the scaling relationships, like how the metallicity should vary with age, how the mass of the halo should vary with the age. They seem to be in very well agreement with the observations. So I'll show you one of these ultra-faint dwarfs being simulated by the edge simulations. And using these simulations, we can discern different components of the galaxy as well. So for example, I'll show you for one of the galaxy how the gas evolves and collides to form one of these ultra-faint dwarf galaxies. We are running from the beginning of the universe to the present day. Present day is close to Z is equal to 0. That is redshift 0. So all the bright patches that you see, they are all the hot spots where the gas is colliding and colliding. And the purple spots are the cold ones. Here you can see a lot of collisions happening. And finally, towards Z is equal to 0, the system appears to be in a quite stable state. And now close to, as we are heading towards Z is equal to 0, we are seeing that now there is some sort of spherical structure. However, it has still some way to reach. So that was gas. Now we'll see how the star particles have come together to form an ultra-faint dwarf galaxy. Right, again, from the past to the present day. So these are different star particles, again, colliding with each other, forming a very unstable kind of bulge. Another bulge coming in, going by, they are undergoing collisions. And finally, they have merged to form one single system, which is quite not spherically symmetric at the moment, but it will be more spherically symmetric as we go towards Z is equal to 0. So this is stars for you. And the good thing about simulations is that although we cannot see dark matter in the observations, we can see dark matter in the simulations. So I'll show you what the dark matter evolution would look like. So unlike the stars, the dark matter particles are a lot. For these ultra-faint dwarf galaxies, these are bigger clumps forming and colliding with each other. All the particles that you see in here, they're all dark matter particles. Again, different dark matter particles are colliding with each other over the cosmic scale to give you the structure that you see. Just like the stars, the dark matter clumps, they also collide with each other and finally settle into a stable state. One thing to notice about this dark matter particle simulation is the scale of these dark matter particles. You can see the scale of the entire bulge is very huge as compared to what you saw for stars or what you saw for gas, for example, which again proves the point that these ultra-faint dwarf galaxies have a lot of dark matter. So this is basically what I do. I use these simulations from edge and getting the results from the simulations, getting the data from the simulations, I compare it with the observations. And for the observations, I'm using the observations from the Hubble Space Telescope. And comparing my simulations with the observations, I want to identify which observables are most sensitive to the observations, which means I want to identify which factors are most important to the galactic evolution in general. Is it the stellar winds which are dominating the evolution of the ultra-faint dwarf galaxies? Is it the supernovae, or is it the radiation physics that is dominating the physics? Once I have an answer of this for the ultra-faint dwarf galaxies, I can be more sure about my galaxy formation models and how it is. Once I know the galaxy formation model for the ultra-faint dwarf galaxies, because they have a lot of dark matter, I can constrain the properties of dark matter from it, which will further help me in constraining the cosmological models, given that dark matter is 1/4 of the entirety of the matter of the universe. So it means that these small galaxies, the smallest and the faintest galaxies, they are not completely useless. In the dance of the universe, these smallest entities, they have such properties that they play the greatest role in overall understanding of the universe. And that was it for my presentation. Thank you so much for your attention.
Right. So that was fascinating. I'm sure there are lots. So yeah, okay. We've only got one microphone here, so we have to be very careful so that we can hear. Lots of questions. Hold on. One second. I'm going to ask Astha as well. I'm going to get very busy.
I was wondering, how different are these from globular clusters? Are they much bigger? And then the other question, sorry, do they have more dark matter than like the Milky Way, like as a proportion of the mass?
A lot more stars. So the amount of globular clusters are basically stellar systems. I hope you can hear me well now. So the globular clusters, they are stellar systems. They don't contain that much amount of dark matter. They're entirely basically composed of stars. As compared to the ultra-faint dwarf galaxies, they don't have a lot of stars in them. What they have a lot is dark matter. I don't have the exact number in my head, but the amount of dark matter in globular cluster is even less as compared to the big galaxies like Milky Way. When it comes to Milky Way, it contains 21 times more dark matter than the visible matter, which means the matter that is present in gas, stars, dust, etc. When it comes to these ultra-faint dwarfs, the amount of dark matter can be 500 to 600 times as compared to the matter contained in your gas, stars, and dust. When it comes to the globular clusters, they're very compact system, almost entirely composed of stars, not of dark matter. So it is the composition of dark matter and the entirety of the compactness of the system that makes the globular clusters different from the ultra.
How do you infer the presence of dark matter in the simulation that you ran showing dark matter combining? So how are you working out the dark matter is there and the quantity and density? Yes, how are you inferring it?
So it starts with very good question and very deep as well. So it starts with the initial conditions that we have for the universe. So the initial conditions of the universe, the picture of the cosmic microwave background that I showed, it basically starts with the assumption that the universe contains 5% visible matter, 24% dark matter, and 70% dark energy. So this is the assumption from the model of the universe that we start with. And how do we know that this model of the universe makes sense? Because scientists think that we have a very good idea of what the universe looked like 300,000 years from the Big Bang. So this image of the cosmic microwave background, it confirms for us the composition of different materials in the universe. So this is what we start with in the simulations as well. 24% dark matter in the entire simulations. And so this is what we start with, and we let these initial conditions evolve. And these initial conditions are evolved in such a way that they lead to the formation of these ultra-faint dwarf galaxies. And in the formation of these ultra-faint dwarf galaxies, we select the systems on the basis of the fact that they contain a huge amount of dark matter as compared to the visible matter. So I would say when it comes to introducing dark matter in the simulation, the presence of dark matter in the simulations, we start with the initial conditions where they're basically introduced, and we just let the system evolve as it is to finally observe a system like ultra-faint dwarf galaxy, which contains a lot of dark matter. And also one thing about these simulations is that they are designed to not produce the galaxies like Milky Way, but to produce a lot of these ultra-faint dwarf galaxies. So what we do is as I show, we start with a very big simulation grid, but we focus on only those simulation methods. We employ only those simulation methods that finally can give us the ultra-faint dwarf galaxies to work with. So yeah, yeah.
So, given we know, and given that we know so little about dark matter, how can you create a predictive model about how dark matter interacts with itself to create those swirling models that you showed us?
That's a very good question. So we know very less about the dark matter, but there are a couple things that we are very sure about. So we work with the model of cold dark matter, which means that the particles of dark matter, they are not annihilating basically each other. It is the cold matter. And what we do is to make sure, so what we do is we start with a certain set of assumptions. For example, cold dark matter. This should be the fraction of the dark matter in the universe. And this is the model of universe that we are working with. For example, the lambda CDM cosmology that we are working with. This, the amount of dark matter, the amount of visible matter, etc. And once we have it, what we do is we match the data, whatever scaling relationships that we get from our observation, from our simulations with the observations. For example, there is a very peculiar property of the dark matter curves to be cold in the center as compared to being cuspy in the center. Maybe I can draw it here if we have a marker. No, I don't think so. We have one. It's still okay. So basically what we do is, it's okay. So what it's still okay. It's still okay. So from the observations, we see that the dark matter, for example, has a chord appearance in the center, which means that if you plot the density profile of the dark matter, it will go like flat and like this, and it will drop the density of the dark matter from the center. This is what we have something from the observations, and this is the kind of result that we can explain with our simulations as well. So starting with the model is a choice that we make for sure. And this is the choice we make, and we compare our choice to what we observe with the observations. And of course, not every choice with this kind of model, like simulating the universe, is no simple task. All the choices that we make, they have their own caveats and stuff. But as long with these simulations, we have been able to explain all those caveats physically with the kind of physics that is in there. And compare it well with the observations, which kind of makes us more and more sure about the properties of dark matter. Yeah.
Is there any evidence for black holes in the center of these extra faint?
Next step. This is definitely the next step that we are trying to implement in the simulations. So the next steps are increasing the resolution a lot more from 3 parsecs to even finer. and also inculcate the effects of black hole physics. But the thing is that even in the observations of the ultra-faint dwarf galaxies, we have not yet observed the black holes in these galaxies. So in terms of what we have with the observations as compared to what we have in the simulations, it's not that far off. But definitely it will be a really good idea to include the feedback physics mechanisms of the black hole in the simulations, yes.
I'm glad I didn't go to the gym today.
One of your slides mentioned that the dwarf galaxy goes across an area around the Earth, 26 light years, million light years, no, 260 light years across, and you compared those two images of very high quality. What would be two areas in our galaxy and the dwarf galaxy?
That's a really great question, because whatever we observe as we look out is dependent on a lot of factors, is dependent on where we are and what we are surrounded with. So when it comes to Milky Way, for example, even if you look from the Earth, we cannot really observe anything towards the center of the galaxy because there is a lot of star and gas and dust which is present. So for example, if you're looking from the Earth, at all the directions, you will hit definitely one direction towards the center of the Milky Way galaxy, where there will be a lot of dust and stars, and your view will entirely be obscured, at least in the visible light. However, when it comes to these ultra-faint dwarf galaxies, they don't have that much gas and dust to begin with. So if you are a system on these ultra-faint dwarf galaxies, most likely for you, if you don't have any dominant neighbors like Milky Way, your night sky will be much more clearer without any dust obscuration and stuff. And at least you won't encounter any effects of dust or any effects of obscuration due to first of all, the size of the galaxy, because it is very small, and the components of the galaxy, which is mostly dark. It is mostly dark matter, not that much visible stuff to begin with.
Not exactly an astronomy question, but I'm curious to know what software language the simulation is written in. Fortran, okay. Well, I was brought up on.
Yeah, I'm guessing most of us were here. So, any more questions? I have one. We had James Binney here last year, and one of the things he said about analyzing the Gaia data was that there was no real evidence for hierarchical clustering. There's no real evidence of sort of small galaxies being absorbed into the Milky Way. In your simulations, you appear to have small galaxies grouped together to form even your dwarf galaxies. So in the observation data, is there any evidence of sort of multiple populations of stars?
Because I would say that the kind of stuff that I'm working with, there is definitely the evidence of not these ultra-faint dwarfs interacting with Milky Way right now, but there's definitely an evidence for these galaxies having interacted with Milky Way, especially in their past lives. So this is exactly like the project that I'm working on. So you see the big galaxies like Draco, Carina, and there is also one dwarf galaxy, Sagittarius. So if you observe, for example, Sagittarius, which is not shown in the picture, it has a beautiful tail, this galaxy. And the tail of the Sagittarius can only be explained by its interaction with the Milky Way, because there are no other massive systems nearby. So they are not interacting with Milky Way as of right now, but they have definitely interacted with Milky Way as to passed by the Milky Way, a portion of their material just being accreted by Milky Way, giving them tail-like appearance or completely stopping their star Milky Way. So there is definitely interaction with Milky Way for these galaxies.
That's great. Thank you. Oh, hold on. You almost got away.
Just thinking about dark matter, is it conceivable that dark matter on its own can cluster and aggregate to create what you might think of a dark matter galaxy all of its own?
Very good question. Okay. Yeah, it is kind of very possible. So we have not, I think I was reading some news articles recently in which they observed like one galaxy, which is just a clump of dark matter, as they assume. But I think we don't have any confirmed evidence of it so far. But essentially, yeah, it is very possible to have just a clump of dark matter on your own. And how is that possible? Once, for example, if I talk physically, it is possible that one of your galaxies, which was formed very early in the universe, we did not have a lot of raw material to form the stars, right? So these galaxies, they formed very early in the universe, had a lot of dark matter, which was the only thing present. And by the present day, all the stars, they evolved themselves, eventually died, and now they are just to us as clumps of dark matter and not any visible matter so far. And so this can be one thing. So evolutionary, it might be possible to have a galaxy which is just dark matter, although we have not observed anything. And this picture that you see in here, all the for the cosmic microwave background, the dots, the red and the blue dots, they're all the density pockets, with the blue ones being denser as compared to the red ones. So it was these initial fluctuations in the very starting universe that led to the instabilities that finally led to the formation of the galaxies. So it's possible that in the very early universe, when there was like no visible matter so far, the clumps of the dark matter just accumulated themselves into those pockets, and these are just very, very small, tiny dark matter galaxies orbiting in the space. And there is kind of no way to observe them, like at least visually, you know. And how would you observe those galaxies? By looking at their gravitational effects. So the stars which might be present, if they're passing by these very, very small dark matter galaxies, they will have, for example, a slightly curved trajectory, which cannot be explained by just the empty space. There needs to be some amount of gravitational source there. So yeah, definitely a possibility, I would say.
Just a fairly foundation basic question, but you use the term collision quite a lot at the start and during your presentation. So what is the significance for research with regard to all these collisions? Obviously we don't see it on we don't see collisions in the night sky, but what is the significance in your research using that term collision?
So when I say the different clumps are, for example, colliding with each other, I essentially mean that there is a lot of exchange of gas and the dust present. I mean, there was no present during the, but there is an exchange of a lot of gas and the other materials between the two systems. So there is essentially a mixing of two systems. And what this mixing can do for you, it can change your initial composition immediately as you mix the two materials. For example, if you mix a stuff which is very rich in metals to stuff which is very low in metals, and you then calculate the properties of a system which is very rich in metals, it won't be that rich anymore because it has aggregated a lot of mass, but it has very low metals. So it is essentially what I mean by collisions. To put it in one line, it means how is it affecting the metals that we can observe with these galaxies. It can be position of gas, the composition of the stars, and the general evolution of the system as a whole. So it is not the collisions, they do not play that big of a role in the present day, but they had a lot of important role to play towards the very starting of the universe, when these systems were just forming. The gravitational system was not entirely stable. That led to exchange of a lot of gas and stuff, etc.
Right, any more? Any from the Zoom attendees? Well, Astha, thank you very much. As you can tell from the questions, I think everybody's really enjoyed your talk and found it very interesting. So thank you very much. Well done.